In this video, we are going to talk about resonance. Resonance is a very important concept in our course because by drawing resonance structure, you can identify where the reactive electrons or the reactive part of the molecule is, and you can predict the products and draw a good mechanism for the reaction. So what does resonance mean? In the definition of resonance, we have a couple of things to consider. Resonance means delocalization of the electrons in the molecule. So the first part to consider is the word delocalization. And delocalization means spreading or movement of electrons. So while drawing the resonance structure, you are moving the electrons. And the second part of this definition is the word electrons. So which electrons are moving? And the answer for that is electrons in the lone pair or electrons in the pi bond. So whenever you see a lone pair of electrons or pi bonds, you can consider drawing a resonance structure for the molecule if it is needed. Imagine that we have an alkane. Alkane has all sigma bonds and all the carbons on alkane is they are sp3 hybridized. So these sigma bonds are forming by overlapping of sp3 hybridized orbitals. So if we imagine that we have two carbons, sp3 orbitals on each carbon overlap with one another to form sigma bonds. And we call this overlapping head-on or head-to-head overlapping. This type of bonding is very strong, so sigma bond is stronger than pi bond, meaning that it is harder to break. Now, if you consider a structure of an alkene, alkene has sigma bond and pi bond. And the pi bond is forming by side-by-side interaction of p orbitals on each carbon. Okay, so these orbitals can interact with one another, and we call this type of interactions side-by-side interaction, which is weaker than head-to-head interaction, therefore it is easier to break. And this is the reason that we can move the pi bonds while drawing resonance structures, because pi bond is easier to move. It's weaker than sigma bond. So it is the same story when we have an alkyne. Alkyne is linear, we know that. An alkyne has a sigma bond and two pi bonds. When do we use resonance? So we use it when one bond line structure of the molecule cannot fully describe the bonding pattern between neighboring atoms. So what does that mean? Let's look at the structure of allyl carbocation. So this carbocation is made of an alkene and a positive charge. That positive charge on a carbon means the carbon lacks electron. So the molecular orbital theory study showed that in the allyl carbocation, we should have two positions that carry that plus charge. However, when you look at this structure that is drawn here, you can only see the positive charge on a single carbon. Therefore, this structure alone cannot fully describe the structure of allyl carbocation. Therefore, we need to draw a resonance structure for that. How do we do it? First, we need to use a double-headed arrow. This is a sign that shows I'm going to draw a resonance structure. And then to draw a resonance structure, what you need to do, as we just talked about, is to either move the electrons in the lone pair or electrons in the pi bond. Here I have pi bond, I can see it. So I can move the electrons in the pi bond and move them between carbon 2 and carbon 3. Now by movement of these electrons, what's happening here? This carbon now gets electron, so it doesn't lack electron anymore. However, carbon 1 loses the pi electrons, so this one gets the plus charge. Okay? Now, if you look at these two structures together, you can see the positive charge is now spread out over two positions, carbon 1 and carbon 3, which can fully match the molecular orbital theory studies. Also, in allyl carbocation, you can see the pi electrons are moving over 3 carbons. This movement, this spreading out of the electrons, we call that delocalization. And in organic chemistry, delocalization is a stabilizing factor. So if a molecule can do resonance, is always more stable than a similar molecule that cannot do resonance. In organic chemistry, we have an arrow, we call that curved arrow, and that shows the movement of electrons. So it has two parts. The tail shows where the electrons are coming from, it shows the source of electrons, and the head shows where the electrons are going to, the destination of the electrons. So the tail shows where electrons are coming from, and the head shows where electrons are going to. So for example, if you look at the allyl carbocation again, our source of electron, we move the pi bond, and this is our source of electrons, so it gets the tail while drawing the arrow, and the destination is between carbon 2 and carbon 3, so it takes the head. And this is how we draw the curved arrow to show the movement of electrons while drawing resonance structures. Now, while drawing resonance structures, there are a couple of things that you need to avoid. The first one is to avoid moving electrons in single bond. We just discussed it, that we can only move pi electrons or lone pair electrons, not electrons in the sigma bond. If we break single bond to draw a resonance structure, we are going to change the entire compound and the connections completely. So if you look at this structure, if I break this bond, I completely change the connectivity here. However, resonance supposed to show delocalization of the electrons in a single molecule, not in two different molecules. The other important point is never exceed an octet of electrons in second row elements. So for example, here in this structure, if I move this lone pair here to draw a resonance structure, what I would get is this structure. Right? And if you look at this structure, the carbon gets more than 8 electrons, which is not allowed. So be careful while drawing resonance structure, not breaking the octet rule. And this is true for the second row elements. We are talking about boron, carbon, nitrogen, oxygen, and fluorine. When using curved arrows to draw resonance structure, we often have one or more formal charges to deal with, meaning that while drawing a resonance structure, you always need to check the formal charges for the atoms in the new structure and assign the proper formal charges for the atoms. A very important note here, the overall charge of the system must remain the same in all the resonance structures. So let's look at this example. To draw the resonance structure for this molecule, what I can do, I can take these lone pair of electrons, and move them here, and also take the pi electrons and move them here. So don't worry about how to draw the resonance structure right now. We are going to talk about it in the next slides. What we are caring about right now is assigning formal charges. So the valid resonance structure for this molecule would be, okay, we've got double bond here, okay, and a lone pair of electrons on oxygen and carbon. Now, this is not the valid structure unless I assign the formal charges for all the atoms, especially the atoms that are involved in the resonance. So let's look at the oxygen. Oxygen has 3 bonds and a lone pair of electrons, so we already know that it is always getting plus charge. Okay. Now, as a practice, we can calculate the formal charge for carbon right here. This carbon gets 0, so I don't calculate that. You can do it at home if you want. So the formal charge for this carbon would be valence electron, number of valence electron, minus number of bonds, minus number of dots. All right, and carbon is in group 4, and it has, be very careful here, this carbon has a hydrogen attached to it. All right, we didn't remove the hydrogen, it is still there. All right, so it has 3 bonds, minus 2, that gets -1. So this carbon gets the -1 charge. And if you calculate the overall charge of the system, it is 0 here and it is 0 here. So this is the valid resonance structure for the molecule that is drawn here.